Hi everyone, I'm going to go through discussion worksheet 6 with you. So the first part of this problem is a number of different alkene addition reactions. So this is where we're adding two atoms across the alkene. So some of the things we want to think about are whether or not we have a Markovnikov or an anti-Markovnikov addition. And then we also want to consider stereochemistry, whether or not we consider something to be occurring by a syn mechanism or an anti-mechanism, or in some cases both. So let's start with the first one here. The first one, we're adding HBr, and here in the instructions it says that assume all reagents are in excess, which means that there's enough of that reagent to react with any number of alkenes that might be in that structure. So for the first one, we have two different alkenes. So we know the net result of adding HBr across a double bond like this is going to be to add the hydrogen to the less substituted carbon and then the bromine to the more substituted carbon. So here what we're going to get is we're going to add a bromine atom to carbon number 2. And we're going to add another one to carbon number 5. And then the hydrogens go then to carbons 1 and 6. So let's first go ahead and draw out our skeletal structure and then figure out what the stereochemistry is going to be. So we are going to add a bromine to carbon number 2 and a bromine to carbon number 5. So now what we see is we've generated two new chiral centers, and because this is going through a carbocation, we're going to have the nucleophile approach either from the top face or from the back face, which means we're going to get mixtures of both. Now we can also know that this mechanism is a mixture of syn and anti, because anything that goes through a carbocation will be. But here, since the hydrogen is being added to a position that already has two other hydrogens, there's no way to show that the addition of H and Br was a mixture of syn and anti. So that's not something we have to consider in this exact case. So instead though, because we're forming a carbocation at both of these positions, we should get mixtures of stereoisomers at that position. So that means we could get the compound where bromine is both forward and then we're also going to get a mixture where one is forward and one is back. But before we go drawing the enantiomers out of both of these, because we should also get enantiomers of both of these compounds, we want to check and see if we have a meso compound, because notice that we do have a plane of symmetry. Sort of a plane of symmetry through here, right? So we have each side has a methyl, a bromine, and then that alkyl chain. So there's some amount of symmetry. So probably the easiest way to determine which one of these is a meso compound is to just determine R and S. So here the priorities are 1, 2, 3. That makes this one R. Here the priorities are 1, 2, 3. That makes this one R as well. That means this is not the meso compound. And if we do the RS configuration of the other one, this one is R, and this one is S. So now this one must be our meso compound. And what that means is we don't have an enantiomer to draw for it, because this one is achiral. If we were to draw the enantiomer, we'd find that it would be a superimposable mirror image instead of a non-superimposable mirror image. So we do need to draw the enantiomer of the first one. And now we have our three products that form in this reaction. Okay, so for the next one, we are adding bromine and water across the double bond. So here, remember, water being the nucleophile in this reaction is going to be the thing that goes to the more substituted position. So the OH is going to end up at this position, and the bromine is going to go here. And then same for this one. OH here, bromine is going to go here. So now what we want to do is first draw out the structure of that product. Now, we know that the addition of Br2 in water, or anytime we do these dihalogen reactions, is going to be an anti-addition. But once again, this is one of those ones that we can't actually tell whether it was a syn or an anti-addition, because we're adding something to a carbon that already has two hydrogens on it. So we're not going to be able to tell that relative configuration here. Now, that doesn't mean we don't have stereoisomers, though. We are going to be able to show some stereoisomers because here we have a cycloalkane. And with the cycloalkane that has more than one substituent on it, we're going to have cis-trans isomers. So that means we can show the substituent with the bromine being cis to one another, and then the hydroxyl groups therefore being cis. Let's just go ahead and redraw this structure. So we're going to have the compound where the OHs are cis and the carbon with the bromine are cis. And then we're going to be able to draw the trans isomer of that. Now where the OH groups are trans and the carbon with the bromine is trans. Okay, so the next reaction is hydroboration. So hydroboration, remember, is our one reaction we know that gives us an anti-Markovnikov addition. So the less substituted carbon is here. So that's where our OH ends up. So remember, hydroboration is really a net addition of H and OH across the double bond. Very similar to hydration with H2SO4 and water, but this one is anti-Markovnikov. So here the OH goes to the less substituted position, and the hydrogen goes to the more substituted position. Now, because this is a syn addition, and we have a cycloalkane where we can actually show that that addition was syn, that's what we need to do. And so here, it's the OH and the H that end up syn in this reaction. So the way we want to modify this structure then is to have both the OH and the H on the same face, so both pointing up. And then we want to draw the enantiomer of that because we know that the hydroboration reagent can initially attack from the top or the bottom, so we're still going to get a mixture of enantiomers. So this will be our other product. And notice in both cases, OH and H are cis, and they are here as well. Okay, so now we're doing hydroboration with a deuterated borane. So here, instead of hydrogens, we have deuterium. So that just means that the hydrogen that got delivered from the boron reagent is now going to be a deuterium. So now we can just modify the previous structure. So we can draw the same products we did for the first one. We don't have to go through the stereochemical analysis anymore because we've already done that. And then I'm just going to make one modification at the very end here. So the modification I need to make is that instead of having this be a hydrogen, it needs to be a deuterium. And notice again here that our OH and our deuterium are cis, and here our OH and our deuterium are cis. So this is still consistent with a syn addition. Okay, so the next one is ozonolysis, or oxidative cleavage. And for these reactions, what we're doing is we're breaking carbon-carbon double bonds. We're cleaving these bonds right here and right here, and we're replacing them with a carbon-oxygen double bond. So first I'm going to give numbers to everything here. Then I'm going to redraw the structure right down here. So I know I'm going to cleave between carbon 4 and carbon 9, and I'm going to cleave between carbon 1 and carbon 2. So at carbon 4 and carbon 9, I'm going to have a carbonyl in its place. So let me go ahead and give numbers here. So at carbon 9, I'm going to draw a carbonyl. And at carbon 4, I'm going to draw a carbonyl. And then at carbon 2, I'm going to draw a carbonyl. And then I can't forget about carbon 1. I need to draw a carbonyl for that. So now I have a starting point to get to the final product here. Now I just have to determine for those carbonyls that actually have a hydrogen on them, do I want to replace it with a hydrogen, or sorry, do I want to keep the hydrogen, or do I want to replace it with an OH group? And that's what we look at the workup for. So this is a reductive workup, so that means anywhere a carbonyl can have a hydrogen, it will, and not an OH. So we're going to put a hydrogen here, here, and here. So now we can just straighten up our structure a little bit and redraw it in the box. So this is carbon number 2, this is 3, this is 4, and at 4 we have a carbonyl. And then we have carbon 5, 6, 7, 8, 9. And at 9 we have our other carbonyl. And then we have that other byproduct, which is formaldehyde. Okay, so the next reaction is dihydroxylation. So this is where we're adding an OH and an OH group across the double bond. And remember that this occurs by a syn addition of hydroxyl groups. So that means the easiest way to draw out these structures is to leave the carbon chain in the same orientation you see it in the alkene. That is, across from left to right, leave that zigzag pattern exactly in the same conformation. Then anything that's hanging off the chain as a substituent like this is simply going to either get pushed forward or back in the opposite direction to where you put the OH groups. So here I'm going to put an OH group forward, which means on the other carbon I have to also put the OH group forward, which means that forces the methyl group back. And then I'm also going to get the enantiomer of this compound where the dihydroxylation reagent approaches from the back. So here I can have my OH back, and then down here my OH would also be back, and that then pushes my methyl group forward. But notice here that in both cases, my hydroxyl groups are either both forward or both back, and so that represents a syn addition. Okay, so my next reaction here is reaction with Br2. So this is an anti-addition. So this is addition of Br and Br in an anti-addition. So once again here, I'm going to go ahead and leave this chain that zigzags from left to right in exactly the same orientation. And then I'm going to make the first bromine forward and the second bromine back. That's how I indicate my anti-addition. And then I'm also going to get the enantiomer of that. So now where the first bromine is back and the second bromine is forward. So here, both bromines are anti, and here both bromines are anti. And so notice we don't form the possible diastereomer where both of those bromines are cis to one another because we didn't get a syn addition. Okay, so the next one, we are adding hydrogen and hydrogen. This is catalytic hydrogenation where we're adding 2 hydrogens across the double bond. And this is a syn addition. And so to some extent, you have to memorize whether something is going to be either a syn or an anti-addition, but the mechanism for these reactions always explains why we're getting a syn or anti-addition. So in hydroboration, the BH3, the hydrogen and boron add at the same time in a concerted reaction mechanism. And so when it's a concerted reaction mechanism, that reagent either has to approach from the front or from the back face of the alkene, but it can't do both at once. And then with the Br2 addition, that's anti because it's a stepwise reaction where first we form a cyclic bromonium ion, and then we do an SN2 reaction to open that ring up, and that's what causes the nucleophile to come in 180 degrees from the carbon-leaving group bond, which therefore gives us an anti-addition. So catalytic hydrogenation is a syn addition, so again, when I draw this out, I'm going to leave that zigzag chain in exactly the same orientation. And then anything that's hanging off as a substituent is just going to get either pushed forward or pushed back opposite to wherever I'm putting my hydrogens. So here, if I put my hydrogen forward, then I'm going to push my methyl group back. And to make this a syn addition, I now have to put my other hydrogen forward. which means now my ethyl group gets pushed back. So notice here, both these hydrogens are syn. And now I'm going to get the enantiomer of that as well. So I'll do the same thing where I leave the zigzag chain from left to right in the same orientation. But now what I'm going to do is put my hydrogen group back. That's going to push my methyl group forward. And once again here, if I put my hydrogen back, that pushes my ethyl group forward. And once again, I've drawn only a syn addition. For the next one, we're adding hydrogen and bromine across the double bond. So this is similar to the first reaction we looked at. So I'm going to be adding a bromine here and a bromine here, because both of these correspond to the more substituted side of each respective alkene. So first I just draw out my skeletal structure, and then I figure out if I have any chiral centers where I can show stereochemistry. So here, this one is not a chiral center because I have symmetry around this ring. But this one over here is a chiral center. So I'm forming one new chiral center, and because it's going through a carbocation, that means I am going to get a mixture of stereoisomers. So I could get the bromine forward, or I can get the bromine back. Okay, so the next reaction is reaction with Cl2 and D2O. So this looks really similar to the one with Cl2 and water. But here the only difference is our nucleophile is deuterated water instead of regular water. And so here it just has a deuterium isotope replacing the hydrogens in water. So here, instead of adding Cl and OH, I'm adding Cl and OD. Now here, remember that the nucleophile, which in this case is water or deuterated water, that goes to the more substituted side of the alkene, so that's where my OD is going to go, and this is where my Cl is going to go. So now here, I'm forming one new chiral center, which means I can't actually show syn or anti, but since we're starting with a planar alkene, those reagents can approach from the top face of the alkene or the bottom face, so we do need to show the stereochemistry of this chiral center. So we're either going to get that forward or back. Okay, so the next part of the worksheet has to do with synthesis problems, and this is something we'll get a lot of practice with, especially once we get into the alkyne chapter. So what synthesis problems are is I give you a starting material that I want you to start with, and then I give you a final product. So what you want to do is select a sequence of reactions that you've learned so far that could take your starting material and convert it into the final product. So this is not in one step, this is generally in multiple steps, and these aren't mechanisms, these are just sequences of reactions that will get you from the starting material to the final product. So it might not be obvious with simpler problems like this, but generally for synthesis problems you want to think of these backwards. You want to look at the final product and look at what's in there and say, okay, well how might I install any functional group I see there, and kind of slowly work your way back to the starting material. And that's called retrosynthetic analysis. We're not going to get into that in great detail here, but I will sort of introduce you to using that concept to solve some of these problems. So let's actually start with problem C. So problem C, our final product has 1, 2, 3, 4 carbons in it. This is really important. You really want to number your carbon atoms when you're doing a synthesis problem, because first it'll tell you where are the new atoms, what are they, at what position did they go, and another thing it's going to tell you, compared to the starting material that is, another thing it's going to tell you is if you either gained or lost carbons. And why that's really important is soon you're going to know lots of different reactions, and so if you're working on a synthesis problem, you might have 20, 30 different reactions to pull from. But if you recognize something like you lost a carbon, or you lost more than one carbon, that means you're breaking a carbon-carbon bond, and that means among all the potential reactions you might use in a synthesis problem, you know you would have to use something like ozonolysis here. So what that does is kind of narrows down the potential list of reactions that are involved in the synthesis. So let's try and number the starting material similarly to what we did the product. So I would say this carbon on the end here looks like carbon number 4, and then 3, 2, and then 1. But what we notice with the starting material is we have an extra carbon, so I'll give this carbon number 5. So this is a case where we lost a carbon, which means we broke a carbon-carbon bond. And that tells us ozonolysis must be involved. Because ozonolysis is the only reaction we've learned where we break a carbon-carbon bond. So that's going to allow us to work backwards. So I'm going to introduce you in lecture into more detail as to what retrosynthetic analysis is. But for right now, I'm going to use a shortcut to retrosynthetic analysis and just set myself up a reaction scheme. This is my starting material. I'm going to use some reaction to convert it to some other compound, and then another reaction to convert it to the final product. Now, if a synthesis problem is more than 2 steps long, you're going to need more of these empty boxes and more of these arrows. But we're just going to start with one for now, because right now the synthesis problems can't be that long in length because we haven't learned enough reactions. So we're going to leave it like this. So to get to the final product, since we know that ozonolysis is involved, the next thing we want to do is figure out what would the precursor look like to give us this product of ozonolysis. Well, there's a couple things we have to think about here. One is that ozonolysis cleaves a carbon-carbon bond and replaces it with a carbon-oxygen double bond. So there's our carbon-oxygen double bond. That means that must have been bonded to a carbon with a double bond. And since we're cleaving a carbon, it means there needs to be a carbon attached here in place of the oxygen. So here, we can replace that carbonyl with a carbon-carbon double bond. This now gives us an additional carbon, so let's number everything. 1, 2, 3, 4. 1, 2, 3, 4, and 5. And do we need more than just that one carbon? Well, if we number our starting material, 1, 2, 3, 4, 5, no, we need exactly one additional carbon. So now what we want to do is fill in the reagents that would allow us to get that ozonolysis to happen. So step 1 is ozone. And step 3, now we have to pick an oxidative or reductive workup. Now notice here, because we're forming a ketone as a product, it actually doesn't matter which workup we choose. So let's just pick one. Let's use dimethyl sulfide, but oxidative workup would work fine here. Now one thing I want to point out is there is another byproduct to this reaction. It's just not shown as the final product. So the other byproduct of this reaction would be this carbon piece here. So when you run this reaction, you would get the desired product. You would also get formaldehyde, and that's where our 5th carbon is coming from. So in a synthesis problem, if what I'm trying to do is synthesize this molecule here, and then I'm not showing you this other carbonyl piece because it's not the important piece, it's not the thing I'm trying to synthesize. So sometimes you'll notice when ozonolysis is used in a synthesis, sometimes this other carbon piece is ignored. Okay, so now we've made our synthesis problem a bit shorter, because now we just need to know how to get from this starting material to this intermediate here. And we know a reaction that's going to directly give us that product. We have an alkyl halide and we want to form an alkene, so this is simply an elimination reaction. So here we could use, there's a couple ways we could do this elimination. So we can do things like E1, or we could do E2. So if we did E1, we would start off by forming this primary carbocation, and then, so that we form the most stable alkene product, we would take off that proton there. Now this, you can see, is not the alkene we want, which means because E1 is going to give us the more stable alkene product, the more substituted alkene, E1 is not going to be a favorable pathway for this, because E1 is going to give us this alkene and not the one we want. So now we know it must be E2. So now with E2, we have a choice of where to put that alkene based on the appropriate choice of a base. If you use something like methoxide or hydroxide, these bases are going to go after the the beta hydrogens that will give us the more stable alkene. So once again, that would give us this. But if we use a hindered base like terbutoxide, now it's simply going to go after the more accessible, less sterically hindered beta hydrogens. So here what we need to use as a reagent is a bulky base like terbutoxide. And so now that's our synthesis then. With this starting material, we react it with terbutoxide, we get to this alkene, and then we do ozonolysis with either oxidative or reductive workup and get to our product. So now let's try another synthesis problem. So here our starting material is this alkyl halide. So let's go ahead and number our carbons. Now you'll see with this carbon chain, these carbons map on perfectly, right? So we have a 4-carbon chain with a methyl group at the 2 position, our 5-carbon. And so here we're not really rearranging this chain at all. We're not adding carbons. We're not losing carbons. So here we're just changing the functional groups that are present and the position of the functional groups. So in the first one, we have a halogen at the 3. And in the product, we have a hydroxyl at the 4 position. So one of the things I usually tell people for synthesis problems like this, where you end up with you start with a functional group in one place and you end up with a functional group in another place, is to take the functional group out and then put the new one back in. So how do we take that functional group out? How do we take out a halogen? We do that by elimination. And the squiggly line on bromine simply means it's a mixture of enantiomers, so where the bromine is forward and where it's back. So of course, if a problem asks you to draw out all stereoisomers, you wouldn't want to use that notation. Okay, so how do we take out an alkyl halide? We take it out by elimination. So we could do an E1 elimination. That would give us the more stable alkene product. And you can see what we ultimately want to do is add a new functional group at the 4 position. That's right here. But right now, our double bond doesn't include the 4 position. So any sort of addition reactions to alkenes can only add to 2 and 3. So then we do not want to do E1 elimination. That means we have to do some sort of E2 elimination. So if we do an E2 elimination with something like hydroxide, that's going to give us the same problems we had with E1. It's going to give us the most stable alkene. So instead here, what we want to do is an E2 reaction with a hindered base, like terbutoxide. And here, if we do a hindered base, we're going to attack the beta hydrogens that are most accessible or least sterically hindered, which will be these ones here, which means now we're going to get an alkene with a double bond between 3 and 4. And that's where we want that double bond because we want to do an addition reaction that adds a new functional group at the 4-carbon. Okay, so now let's go ahead and continue on here. Let me just write it out more cleanly. We're going to take this alkyl halide. We're going to do elimination with terbutoxide to give us the less substituted alkene by using a sterically hindered base. That's going to give us this. And now what we want to do is we want to add that new functional group at the 4-carbon. So how do we do that? We now have an alkene that goes between carbons 3 and carbons 4, and we want to put a functional group at the less substituted side of the alkene. That means we're doing a anti-Markovnikov reaction. So the only way to get a functional group at the less substituted side would be to do a reaction that's anti-Markovnikov. So here, the only anti-Markovnikov reaction we know is hydroboration. And luckily, that's exactly what we want to do here, because if we do hydroboration, we're going to put an alcohol at the less substituted side of the alkene. And so this is our final product. So that's our completed synthesis for part B. Okay, finally we'll go to part A. So here our starting material is this alkyl halide. And then our product here looks like this. So let's go ahead and number our carbons. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So notice in the starting material, carbon 2 is bonded to a carbon 1 and a carbon 5, and it's the same in the product. What's different is that at carbon 4, this is the one that contains the halogen in the starting material, but it's carbon 2 that contains the halogen in the starting material, in the product. So we need to move the halogen from carbon 4 to carbon 2. Okay, so how do we do that? Well, generally we said if we have a functional group that's now in a different position, we take it out and we put it back in. So let's do that. Let's first take it out. How do we take out the halogen? We can do that by elimination. Now here we can't do E1 elimination. And here it's because we have a primary alkyl halide. So for E1, you need to form a carbocation. But if we have a primary alkyl halide, we can't do that. So E1 is off the table. Now E2 is difficult on a primary alkyl halide because you remember primaries normally give us SN2 instead. But the way around that, the way to give us an E2 reaction instead of an SN2 for a primary, is to simply use a sterically hindered base. So recall in the previous synthesis problems, we used the sterically hindered base to pull off the most accessible, less substituted beta hydrogen. And here we're using it to just give us E2 in general. We only have one set of beta hydrogens. But the problem is with a primary alkyl halide, they're more prone to SN2, and so we use here the bulky base for a different reason than we did in the previous problems. Here we're using it to simply get elimination over substitution. So the product of this reaction is going to look like this. And now if we keep numbering our carbons, now we want to add our nucleophile, or we want to add our new group to the 2 position. So this looks problematic, right? Because we don't have an alkene at the 2 position. We have the alkene at 3 and 4. So how are we going to get something to attack at the 2 position? Well, let's first think of just how we would put in that chlorine group. We would put in that chlorine group, if we have an alkene, we could put in that chlorine group by reaction with HCl. And we know that this undergoes an SN1 mechanism. So even though right now it might look like the chlorine is going to go to carbon number 3, sorry, I should say an SN1 type mechanism. Here it looks like the nucleophile would go to carbon number 3, but let's on the side here draw the structure of the carbocation that would form, because remember HCl is going to protonate the double bond and form a carbocation. So anytime you're trying to predict the product of something like that, you want to draw the carbocation and see if there's going to be any rearrangements. And here, there's going to be a hydride shift. If we shift this hydride over here, then we get the positive charge here. And now, where's the chlorine atom going to attack? Now it's going to attack right there. And that's exactly where we wanted it to go. So now if we just react with HCl, oops. We're going to get the desired final product. So now this synthesis problem is complete. Okay, so let's go down and do the mechanism problems. So the first one says, draw an arrow pushing mechanism for each reaction shown below, include all non-zero formal charges. So let's go ahead and do that. So we have an alcohol functional group and we have an alkene, and then over the arrow we see Cl2. So we don't have any reaction where alcohols react with Cl2 directly, but we do know a reaction where the alkene reacts with Cl2. And the way that it's going to react is going to be the pi bond is going to react with one of the chlorines. It's going to allow us to kick off the other chlorine. And then we're going to bring these electrons back down to the other side of the alkene. So that is our chloronium ion intermediate, and we also form Cl-. And normally what we do is we have Cl- attack the more substituted side of the chloronium ion. But here, if we do that, you can see it's not going to get us to the right product, because doing that would give us something like this. Right? But that's not what's forming here. It's forming a ring. So remember, we can react Cl2 with water, and if we do that using water as the solvent, water can act as the nucleophile. So here, instead of water, remember what part of water actually reacts? It's the lone pair on oxygen. And here in this compound, we also have a lone pair on oxygen. So we're going to use the lone pair on oxygen here to open up this ring. And notice here, I'm attacking the more substituted side of the chloronium ion, because remember, that's the side that's attacked due to a more stable no-bond resonance structure. And what I get as a direct result is this. So now the final step is simply to deprotonate, so I can use chlorine as my base. pull off that hydrogen and form the neutral product. Okay, so the next reaction is a reaction with HBr, and right off the bat, we can see that we go from a 4-membered ring attached to a 5-membered ring to a 5-membered ring attached to another 5-membered ring. So we can tell here we're going to do some sort of carbocation rearrangement that's going to change around the carbon skeleton and do a ring expansion. So first things first, find the functional group that's going to react with the reagent that's shown over the arrow, and that is the alkene, which is going to react with HBr. We're going to form a secondary carbocation, and at this point, we're going to do an alkyl shift. So to go from a secondary carbocation to a tertiary, we can shift one of these alkyl groups here. And down below, I'm going to try and walk you through this a little bit more. Let's just draw that carbocation again. So here we want to shift one of these alkyl groups, right? So here what we can do is erase the bond that we want to shift. So we want to shift this bond here. We want this carbon here to form a bond to this carbon. So we want it to take its electrons back from this bond, thus giving this thing a positive charge. And then we want to give the electrons in that bond up to the one where I'm drawing the dotted line. So here what we could do is just erase the bond we want to break. And then form a new bond to this structure here, or to this carbon here. So now I'm just shifting that bond. It used to be right here, and now I'm shifting it up this way. So in doing so, I'm now going to leave a positive charge here, and the positive charge up here is going to be gone. So now we can just draw that out in a nicer format, which is what I'm going to do up here. And if I number everything, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. So now we can see where our methyl group goes, and our positive charge is here. Okay, now the last step of this is to do a nucleophilic attack with bromine. Now that we've rearranged to a more stable tertiary carbocation, and we have the ring system intact, so notice now we have that 5-membered ring and that other 5-membered ring. Now we can react with Br-. And that gets us to our final product. Okay, so our last mechanism problem is reaction of an alkene with HBr. So we know that generally HBr is going to react with alkenes to put a hydrogen at the less substituted side and the bromine at the more substituted side. And this is because we're going through a carbocation. So here we have 3 alkenes, and each of them is capable of forming a tertiary carbocation at these carbons here. Another thing to notice about these 3 alkenes is that they're completely symmetric. So it actually doesn't matter which alkene we decide to react with first. So let's go ahead and redraw our structure so we can start doing our arrow pushing mechanism. Because all 3 of these alkenes are symmetric, which means they are all going to give a similar product upon reaction with HBr, it doesn't matter which alkene we decide to react with first. So what I'm going to do is react this first alkene over here on the left with HBr, but again, it does not matter which alkene I choose. So the alkene is going to react to get protonated, leaving us with the positive charge at the more substituted position because that's the more stable carbocation. And the next step for these reactions is normally that we can simply react with the bromine nucleophile. But there are other things in here that can act as the nucleophile, for example, the pi bonds. So one of these other pi bonds could now react with the carbocation carbon to form yet a new carbocation. And here remember that carbocations are essentially Lewis acids in that they have an incomplete octet, and they can react with any Lewis base, and pi bonds are Lewis bases. So we can react a pi bond with a carbocation to form a new carbocation. So if we react this pi bond with this carbocation, what we would get is something that looks like this. So that's just showing you the general idea here behind the reactivity that's going on. So that means we can react one of these other pi bonds with the carbocation we just formed. So if I react this pi bond here, I'm going to label this carbon 1 and 2, with the carbocation, which carbon is going to form a bond to the carbocation? This carbon is going to form the bond to the carbocation because in doing so, the carbocation is going to go on carbon number 2, the resulting carbocation. So if I formed a bond at 2, I would be putting the carbocation at 1. But if I put the carbocation, if I form the bond at 1, then I'm going to put that positive charge at the 2 position. So now I'm going to go ahead and number. If I know I'm going to form the bond at the 1 carbon, I'm now going to number 1, 2, 3, 4, 5, until I hit my carbocation at 6, because that's going to tell me the size ring I'm forming. So now if I have this pi bond react with the carbocation, I now can see that if I'm forming the bond between 1 and 6, then I'm forming a 6-membered ring. Oops. So now if I number those carbons again to correspond to what I had before, this is my 1 carbon. My carbocation ended up at 2. Then I have 3, 4, 5, and 6. And so that's how I can tell where all the substituents are hanging off of this ring. And now I just need to put my positive charge. My positive charge is down here at the 2 position. And now I can continue on. So now what I can do is I can form yet another ring structure by reacting my remaining pi bond with the carbocation carbon at the 2 position. So now when I wrap that around, I'm forming another 6-membered ring. And so now I can draw this out. So I'm going to draw my first ring structure intact. Then I'm going to draw my new ring structure coming off this way. And now my methyl group is going to be at this position. My other methyl group is right here. And now what I have is a positive charge right here. So now that I don't have any remaining pi bonds to react in this structure, now the only nucleophile that's left is Br-. So now the Br- is going to attack that carbocation carbon. And that's how I get to my final structure. And now we're done.